Hello everyone, my name is Darshil Chaudhari. Today we will discuss the topic of fire spread by modeling it using cellular automata. So these are the group members, Meet Sable, myself Darshil Chaudhary and Nisarg Bhalia. For modeling this process, we have taken a few assumptions. So first of all, we have used one of the most popular techniques, that is cellular automata, to model this process, as it can predict the complex global space dynamic evolution through a set of simple local rules. As you can see, we all also have tried to implement one of the very popular examples of cellular automata, that is game of life. Though we could have used the Moore neighborhood structure to keep it simple, we have used the von Neumann neighborhood structure. Lastly, we have used the periodic boundary condition to make it look like an endless or a boundaryless world. Now that we have set up the problem and basic assumptions, we will discuss how we have set up the grid. So first of all, the cells of the grid will only have three values, that is empty, meaning that there is no tree at that cell, tree, meaning that there is a tree present at that cell, and burning, meaning that there is a tree that is burning at that cell. Now, to initialize the cells with these values, we will employ two probabilities, that is the prop tree, which is the probability that a tree initially occupies a cell, and another is the prop burning, which is the probability of the tree initially burning if a tree is present at that cell. Now we will traverse the whole grid, and for each cell we will generate a random number, and if it is greater than the prop tree we will define it empty, else we will generate another random number, and if that number is less than prop burning then we will define it as burning, else we will define it as tree. Now that we have completed the initialization of the grid, we will now discuss the rules following which the spreading of the fire will take place. So these are the four rules that will lead the simulation. If a cell is empty, it will remain empty in the next time step. If a cell is burning, it will become empty in the next time step. The third and the most important rule decides how the non-burning tree will catch fire. For that, we have employed two new probabilities, that is prob immune, meaning that the probability that the tree will not catch fire, and prob lightning, meaning the probability of lightning hitting the site. If there isn't any tree burning in the von Neumann neighborhood, then the cell will remain as it is, else we will generate a random number, and if it is less than prob immune, the tree occupying the cell will remain as it is, else it will burn. This tree can even burn if there are no burning trees in the von Neumann neighborhood through lightning. Here we will again generate a random number, and if it is less than prob lightning, the tree at that cell will burn, else it will remain as it is.
I am Meet Sable. Uh, I will continue from where Darshil left off. So this is the simple implementation of fire spread cellular automata. We can see the simulation itself. The green denotes a tree, red denotes a burning tree, and black denotes an empty cell or a burnt tree. On the right hand side, we can see the timestamp of the current frame, total frames, speed of the simulation, state of the simulation, it's either play or pause, and the wind if there is any wind. This can be controlled via keyboard inputs. These are the graphs for the simple fast spread model. First graph shows the ratio of initial density and final density on the y-axis, and on the x-axis it is the density of the trees. We can see that as the density of trees increase, more trees are burning, and after around 0.7 density you can see that the line are getting parallel, more and more parallel to the x-axis. That point is called a tipping point. After the tipping point, it isn't changing as much as it was before, so the line seems parallel to the x-axis. And the graph on the right hand side is of the forest density after the fire is burnt versus the initial density of the trees. We can see that the density increases in the beginning and then starts falling off and attains a somewhat constant value parallel to the x-axis after the tipping point. This is the improved model. In this model, we are considering that the tree takes 2 steps to burn, and the burning of a tree is proportional to its neighbors. Like, uh, if more neighbors are burning, then the probability of the current tree burning is higher. In this model, we can see that the tipping point is at around 0.65, after which most of the trees are getting burned and the density is nearly zero. This is the model with the wind direction implemented. In this simulation, the wind level is 1. We can see that the fire is spreading in the upward direction more considering to the other directions. The nature of the graphs is similar to the previous graphs, but we can see that in the first graph ratio is decreasing faster than the previous models. On the right hand side, we can see that the initial increment is similar, but the decrement in the end is faster than previous graphs, and the tipping point in this graph is at around 0.75 density, as we can see in the graphs. This is the same model as previous one, but the wind level is taken to. The wind effect is more prominent in this model compared to the previous model. The nature of the graph is similar to the previous graphs, but the tipping point is slightly shifted towards right side at around 0.8, and the drop in the right hand side graph is not as steep as it was in the previous model. This is the model with a varying wind direction, and the wind level is of 1. We can see on the right hand side that the wind is changing after a certain amount of steps. That step is also varying with the time. The nature of this graph is also similar to the previous graphs, but tipping point is slightly shifted toward the left side, and the density and the tipping point is at around 0.75 density in this model, and the forest density after the fire and initial density graph is nearly similar to the previous models.
My name is Nisarg Bhalia. So, we conclude this lab with the following conclusions. So, we observed the fire spread cellular automata model with different initial conditions. We also observed that the tipping point is more to the left when the fire is spreading fast. We observed that the tipping point was about 0.65 the initial density of trees in the improved model. Also, when the wind is considered, the amount of trees burning is increasing faster compared to the other model, and yet faster when the wind level is increased. Also, with varying wind direction, we observed similar results as to the normal wind model. Thank you.